presuming that you know Revit pretty well and you also can get around to Dynamo and do automation, the next step of kind of supercharging on top of that is, sometimes it's kind of a pain to use a visual programming environment. It's just easier to write code. So we're going to get into some of that. So it's a little bit of high level, hand wavy, look at the world, it's awesome, and then a little lower level, here's how you actually start to build the stuff. Hopefully by that point, we'll have a longer HDMI cord that I could use to actually drive Revit and Python and stuff without looking at the wall. So as Shima said, my primary role at Tesla is kind of a senior staff software developer. I've got about 20 years of software development. I'm an architect by background. I'm from the Philly area, grew up in Wilmington. My wife is from Lawrenceville, so we live up in Bucks County, so we're pretty close. And at Revit, or at Autodesk, I worked on things like Revit, Dynamo, Project Vasari, a lot of kind of sustainability kind of things, and computational design, and then more recently, generative design, which is really just a fancy way to say, declare what your goals are and figure out, use the computer to run through many, many options to figure out how to achieve your goal. So, and that's what I'm doing at Tesla. So, what we're doing at Tesla is using Revit and Navisworks, along with CATIA and SolidWorks and Inventor and a bunch of other tools to connect all the way through from early design of cars all the way through planning of the machines to make the machines, if you think about it that way. So we have to build factories and assembly lines and production pipeline to make cars as cheaply as possible. And it's super automated. And that's why we're using a lot of these tools. So the overall talk that I was talking about was really about observation. So figuring out your current environment, predicting the future, and then evolving your current state to get there. Does it look like the webcam is working okay? Like the recording?
Yes.
Okay, cool. So yeah, when you read anything about the news, you hear machine learning on a daily basis. You hear scary things about AI. You hear happy things about AI. AI is not new. This is the first one of the first autonomous driving platforms. This was built back in early 1992 at Carnegie Mellon. When I was, while we're doing a little quick change, I will talk about automated cars as a proxy for this idea of AI and machine learning, where we hear a lot about these tools being used for good or for evil, if you think about it that way. And the fact of the matter is they're neither, or they're both. And they're nothing more scary than math. Like if you hear anything about machine learning or artificial intelligence, just substitute statistics, and it makes a lot more sense, because it's like statistics is not going to take your job. Like AI is not going to, automation and AI are not going to take your job. All these things are predictive models to help you understand and come up with a better solution to a problem. Rewind back to like 5 minutes of technical difficulties. So math isn't scary, AI is just math, machine learning is just math. This is some math that was done 27 years ago. That's the same problem. Okay, I might just not be able to play in full screen. Okay, well, that'll be fine. It's so weird. So big honking machine. It's a deuce and a half, like a big Humvee, like with a supercomputer basically on the top of it, laser rangefinder, driving through Schenley Park in Pittsburgh and freaking out joggers like on a daily basis in 1992. This is one of the earliest platforms where people are actually using machine learning on top of a computer vision system, which was like, you remember back when like webcams were like 640 by 480 or even smaller than that. Like the very first like little web like video that you saw, that's pretty much the eyes that this thing had back in the day. And you know, it was basically what the same kind of platforms people are using today, where the machine is not driving, it's watching. And all it's doing is making an inference, making a predictive guess about what it sees on the webcam and what the driver does. Like it instruments like, you know, the accelerator and the steering wheel, and that's all it sees. So literally this like itsy bitsy blocky image is the level of resolution and the level of information that was coming into a platform that was driving a very scary, large military device. And that's where things started. So the researchers that were doing the math that was driving the computer code to drive the car are now in charge of things at Google and Facebook and Tesla and Amazon and Apple, building whole new platforms like this. And all the press that you hear about, things, autonomous platforms that are evolving are not sentient, they're not reasoning, they're not thinking about the world in the same way that we are. They're literally just doing math faster than we can. And it's changing a lot of different industries, like not just autonomous driving, it's just kind of a good proxy for that. And then here we are today. So this was actually 1997-ish, or 2017. Tesla Model S has about 20 times the number of sensors and about 200 times the amount of compute power, and it basically can drive autonomously to the same degree that you would think, right? So, it'll follow lanes, it'll course correct for you, it'll figure out obstructions in the road and that kind of thing. So the level of, I like to think about it as like decreasing the cognitive load that you have, like when you drive. Like we all learn to drive when we were, 15 or 16, and you're learning how to course correct and sort of take all this input in all the time. And all this, at some point in time, you can actually talk and chew gum and like listen to the radio and like not crash into things at the same time. And have kind of higher level thoughts like while you're driving. Like I like to drive because I can just kind of zone out and like just think about things while I'm driving. I like the act of it. But if you didn't have to do all those little itsy bitsy movements all the time and course correct, you can free up your kind of executive function and kind of more of your brain power to do other things. So that's kind of a good proxy for how AI and machine learning and computer vision are going to change our lives just in general. The little things that take a lot of time you won't have to think about it anymore, it'll just kind of happen, or you'll still be in control of, you'll still have mastery and autonomy of, but you can kind of send your minions out to do something along the way. So it's not robots are going to take your jobs, it's robots are going to help you do your job better if you can master these techniques, especially from the design sort of domain that we're in. There's a lot of opportunities, right? So if you think about the pressing industry sort of demands and kind of demands that we have out there, things like climate change, population, and urbanization are kind of the big factors that are addressing the built environment and the things that we're doing on a daily basis. So the kind of the biggest challenge or sort of posit that I would have is how can we use some of these tools to help us build better buildings, ultimately help us design more efficiently, and that's kind of what we're doing, both at Autodesk and at Tesla, and kind of where the world is going. Let's see if this actually plays. I'll just have to do it here. So some of you have probably seen this model before. This is a simulation from NASA that's using satellite data that looks at the world kind of flattened down, but it's looking more particularly at particulate matter in the atmosphere. So things like smoke, salt, and dust, and how they propagate through an observed means, but also how it can be simulated using supercomputers to figure out how things happen. So this was 2017, which was a pretty crazy year for storms. Here's Hurricane Harvey evolving in the Gulf, right there hitting near Houston, and you can start to see the litany of 5 or 6 other major storms that will pop up throughout the summer, literally like 2 years ago, right now. So you think about how things have changed over the last 60, 40, 20, 10 years as far as weather reporting and simulation, and how that's affected our society and for the better, right? I mean, if you can understand, hey, there's a storm brewing out in the Atlantic, we should probably move people away from North Carolina. That's a good thing. You can save lives, you can save property, that kind of aspect of it. Early warning, I mean, obviously things like Maria, like these are the ones that hit Puerto Rico and the Virgin Islands. They were massive. There's no getting away from these things. They're going to hit. But if we can use computing power and prediction to forecast more efficiently, all the better. But how can we do this at a longer term and a longer range process to help us understand how our climate and our environment are changing across the board? climate change is real. I don't think anybody here is going to dispute that. It's happening. Our world is changing. So how can we use computers to help us understand how our local environment is changing, how the climate is changing, and how we should design differently to address those needs and to better serve our customers and the environment around us. So that's definitely where I've been spending a good deal of my time over the years, is helping building tools to help that from a climate standpoint, and also from, like it or not, when we build new things, you end up, if you don't think about it and do it intentionally, it's going to end up looking like this, where it's basically sprawl. Kind of the urban density is increasing. So how can we understand and model and predict the impacts of any of the small changes that we're doing at a macro level, right? So buildings are a system, and they're composed of smaller systems, but they also can be thought of as being part of a bigger system, which is the city or the town or the community that you're in. So if we can model that, if we have ways to sort of treat these things like objects that we can understand how they behave and model them and predict how what is the impact of building a 14-story building, next to a park. Well, we can simulate that. We can understand how it's going to work, and we can start to address any of the potential downsides of any of our design solutions. So the fact is, these are some numbers that are not new to anybody here too. By 2050, 10 billion people, about 7 billion of them will be in sort of an urban situation, sort of similar to where we are in Philly or DC, kind of the megalopolis of New York, DC kind of axis. A lot more middle class as well. So you think about like the mass movement of people in China and India and other places like Brazil. They all are moving to a more urban situation. They're all going up as far as their socioeconomic situation, and they all want iPhones and refrigerators and cars and everything else. So the demands that puts on the built environment that we build are quite profound, and they're just going to increase. So the changes that we've seen are just going to start to ramp up even more in our lifetime, right? So, I think probably most of us will be still working in 20 years or 30 years. So hopefully we'll be able to continue to address some of the challenges and issues that we have. And the benefit of using computation to do that is it opens up your eyes more broadly. It helps you see what you can do and come up with a better solution, and help people understand the impacts that might not be as aware of what's happening. So the fact is, we're not ready. Talked about this. Buildings are systems. They live in a bigger system of a city. This is an analysis that we were doing at Autodesk, looking at Carleton University near Toronto as a proxy of this, right? So as you develop new buildings on a campus, say for example, you can throw all the smart sensors and sort of great building systems that you want into it, but if they don't actually have a net benefit for the larger community around you, then what's the point? So what we were doing here is looking at not just a new building or a set of new buildings on campus, but looking at the energy flows throughout that whole system. And how can you start to look at, well, there's a lot of heat being generated in this particular lab. We could actually use that to funnel in and serve the heating demands for another building that we're putting together, like a residence or something like that. So you can start to address kind of the overall net energy and start to look at the larger loads, and more importantly, start to forecast how your system is going to perform. There's actually a startup even, and I met them. They're coming out of Penn, like I met them last summer. They're doing machine learning statistical models of energy use for a place like Penn or a university campus to start to hedge, basically. So large campuses do like energy contracts, and when you hit like July and you spike past what your predicted demand is going to be, Pico or whoever else is going to come in and say, well, you owe us another $100,000 like for the month. Like it's not like $100, it's $100,000. So how can you start to model that out from a demand standpoint and start to basically predict and evolve your financial model as well as your building performance model for these campuses. So again, like you don't want to get caught blind by these. You want to start building in design models and operational models that are benefiting you in the long term. So same kind of thing happens at the larger macro scale. So this is a model of Paris. using some of the tools that we were making at Autodesk. And not only can you do sort of large GIS level databases, but you can start to overlay other metadata on top of it. You can start to look at demographic information. You can start to look at other kind of transient information, like where are traffic accidents happening, like how far can people walk in 5 minutes, and can they actually use the metro? This kind of thing that typically is the urban planner kind of domain, you can start to use as a design tool, as an informational tool as well. Starting to do things like predicting, like, gee, if the Seine floods, what's the impact going to be? What kind of critical infrastructure, or how will this impact like the buildings that we're working on along the way? This kind of modeling power and simulation power wasn't available 10 years ago or 5 years ago. So how can we start to use that to our advantage, to observe, predict, and evolve? It's basically the premise here. And these don't require like a PhD to do anymore. Some people have been doing more of this over the years and others. Where it gets into interesting work around machine learning and AI and generative design, quote unquote, is if you can start to not just look at what's there now, but look at the impacts of what you're changing, and more importantly, starting to set goals. So I mentioned before, generative design is kind of a dumb term. It should be like goal-driven design, or kind of declaring clearly what your goals are. So in this case, you can play what if using this little tool that a colleague of mine made that says, I want to increase my percentage of parks. I want to increase my setback from the road. And what is the impact going to be over at the built environment if I start doing that? Because the system is generating a possible future based on what you tell it. So in this case, like many of these cases, you're not actually descriptively modeling. You're not saying, I'm going to go to Revit or AutoCAD or whatever and model a box. You're saying, I want this road to get this much light this amount of time during the day. Figure out the box that will achieve that goal for me. And that's what a lot of these situations are here. But the problem is we don't have a good model for how to describe these goals. Like we didn't learn, at least I didn't learn in design school, write down these goals clearly and determine a metric to see if you have achieved them or not. Like that's a level of rigor that when you're just learning how to sketch and like draw a floor plan, like people don't usually do until maybe typically like in grad school or something else. But like how can we start changing our design process to more effectively declare these things and have clear conversations like with our clients and colleagues about how to do that? That's kind of the larger challenge that I see in the industry right now, and definitely one of the things that I've been working on trying to fix. This is like hamstrung. Like how do I advance these things without messing something up? So that's where we get into the optimization and goal setting kind of discussions. So kickstarting Revit and kind of adding goals and logic on top of Revit is where people are going right now, or Rhino and Grasshopper or something else like that. But if you can do something like take a typical floor plan and model how people are going to flow through that space, and simulate the interactions that people have during the day. Like I might talk to Ryan 5 times in one day as I'm going to get coffee, or I might actually have some intentional conversation with him too, focused and as we do design work. But you can start to simulate that behavior and understand, is that a goal? Like, are we trying to help people understand how to interact with each other and build build an environment that's conducive to that, or is it trying to solve for a different type of goal? But in models like this, you can actually literally do path planning and figure out like where are the sort of where's the heat map of where the most people are going through. Do things like sightline analysis, visual connection to the outside, adjacency, obviously, kind of planning along the way, and you can start to clarify like what trade-offs there are, because many times like these things are competing with each other. Like you can say, I want to have like the lowest cost per square foot, the highest density, and the tightest connection to the outside world, and increase like buzz or some kind of loose word like that. Like, well, those are kind of like competing with each other. Like you can have a great environment that allows people to focus. It will probably just cost like more money because you need more partitions and things like that. So that allows you to have that kind of structured discussion with the client that says, you say you want to help people collaborate, or you want people to focus, or that kind of thing. Like, how can we start to use these tools to help do that along the way? These things can also be used, so that kind of model can be used at the sort of architectural scale or even at the urban design scale. Like in this case, this is using this planning tool to come up with a better connection for like a master plan. And basically, like, the design team kind of went back to the owner and said, we want you to write a brief that isn't about like the description of the space, it's about what are the goals you're trying to achieve like in that space. And it's about having a couple different roads that come into an axis and like what they want to be achieved out of that as far as traffic circulation and pedestrian circulation, things like that. And then we're able to like run literally a model that might work. Let's see. Yeah, that went through many options of like how to lay out this type of space. So it's just a parametric model that embodies the design inputs and then the rules that are trying to be measured, and then runs through like a lot of different options and evaluates them along the way. So this is more building a parametric model, flexing it, and then more importantly, like looking at the results and weighing them against each other and taking the best of each of these options from there. So that's just some of the logic behind it. Just fast forward through this, but yeah. Let's go to the next one here. It's the same one. So there's another interface that basically shows like how to look at the results and say, here's why this one is performing better than other options that are out there. So these are kind of closed form solutions if you think about it that way. It's a parametric model. All you're doing is just running it through like 1,000 different options, coming up with the best answer. But in all these cases, like you're declaring a goal, but you have a starting point that you've come up with too. And that's, if you're using Grasshopper or Dynamo or, sort of any evolutionary solver, that's kind of the process that you're going through like right now. Where things get interesting is if you can go beyond that and not have to be like the computational design person or like the PhD guy to do that anymore, person to do that anymore. And that's where machine learning comes in, one thing that we think is pretty interesting is this sort of observational approach where I'm going to sketch 12 different floor plans and I want you, the computer, to watch what I'm doing and learn from what I'm doing and simulate that or emulate that. That's kind of a lot of the research that's happening these days. This is a colleague of mine, Nono Martinez Alonso, who this is his thesis work from Harvard from last year, 2 years ago. And what he did is come up with a dialogue with the computer. So he sketched a tree or sketched other things, and the computer looked at the sketch and said, I think you're drawing a tree. And this is the kind of tree that I think you're drawing. So it's guessing based on the inputs using a machine learning process. And that can be applied to many of the design practices that we do in a way that is provoking conversation or dialogue. It's not scary, the thing is going to take your job. It is helping you or watching you or advising you along the way. So these things, a lot of the research right now is, I think you're drawing a facade, I think you're drawing a floor plan, I think you're drawing, a Gropius house or some kind of Palladian villa, like all those kinds of like sort of idiosyncratic, like, yes, I can look at that and determine what kind of floor plan or what kind of building this is, are the type of work that's being researched right now. But that could be taken further and say, I see you're looking at a commercial bathroom with this many stalls and this many ADA requirements. Would you like me to design that for you and spec it out for you? Those are the kind of things that you can do with this now. Like I literally had an intern that was doing that like last summer. So what kind of like rote tasks could we have the computer start to do, because our medium is so visual and is so code bound and procedurally bound? Like these are not like, it's not rocket science to do. It's like actually a lot easier than rocket science to do this stuff. And as we were saying before, you don't need a supercomputer to do it. Like these are libraries that Google made open source like 3 years ago, and that other people have built things on top of. And you can literally, for 2 cents an hour, pay Amazon to run for you these days. So So that's kind of an interesting model. And if you imagine, like literally you have an electronic sketchbook that as you're sketching, it's trying to help you determine, or answer a question that you might not have even posed in an explicit way anymore. So that's the kind of thing that we think is interesting, could be scary, but I think it's pretty cool. And then the cool thing is, this is how you program that. Like all you do is you sketch and it learns. So you don't have to write code, you don't have to do anything along the way, which is, again, like more approachable. This is a training set that you feed into the computer to help it learn how to identify a tree, for example. So I really like this quote. So by curating a data set, the designer is the programmer. Choosing the right set of images becomes part of the design process. So you're, in the same way that you do like precedents or kind of look at examples, like if you just start feeding them into a computer or having it simply watching over your shoulder, it can start to help you along the way. So, so that's kind of the larger highfalutin design idea. This also gets into materiality. I mentioned this campus before. It's not just at the design phase, but it's actually all the way through construction and commissioning and operations. So this is a live model. So using a Revit model, basically, that was exported to the cloud, but more importantly, tied to a crap load of sensors that are in the actual building. Like you can start to use the Revit model as a live link to the actual performance of the building. So when you're working with or any mechanical engineers, in the room, mostly architects and structural people, looks like. Okay, well, now we can make fun of the mechanical engineers. So, so your mechanical engineer has set points for the model. It has like an operational sort of a process that they've gone through to determine how the building should be commissioned. And that's usually very well thought out. It's considering very good practices around sustainable design and LEED. Then you end up with literally the operations guy sitting in the basement trying to program like the boiler, and it just isn't, even with commissioning and everything else, like it doesn't usually work the right way. Or you have people in the mix, like where people leave windows open for the whole weekend, or there's very many people that are cold or hot. Those are not well modeled in energy simulations. So inevitably there's a simulation and then there's reality, and they don't often meet. So what you can start to use is these tools to observe reality and change the simulation along the way. So the same way that machine learning tools that I mentioned before are observing reality and helping people drive, you can use them to help drive your buildings. So that's kind of the next level of operational kind of opportunity that we see here. People like Kieran Timberlake have been doing these things for a while of putting sensors on everything and collecting a whole lot of data. But the idea now is, what do you do with that data? And how do you use it to ultimately get better answers and better operations? So this is the actual data coming in from a sensor in the building somewhere. Can't really see exactly where. And you can start to say, is that in line with what you're thinking or we're supposed to be or not? And collecting that over time. We're also seeing this in construction too. So using machine learning, take a look at your RFI log or your sort of any issues that come up in a particular building process. Can you start to learn from the patterns of that? It's a little tough in this industry because of the transient nature of how people work together, but there are startups that are trying to do this now to start minimizing risk for owners. So it's a whole other process. So getting back to coming full circle, those are the kind of larger opportunities at the macro level, at the building level, and at the sort of smaller level for machine learning and computer vision and AI, if you will, to help us. And this is how we're starting to use these things at the Gigafactory and in Tesla as well. So I mentioned I used to work at Autodesk and run software development teams. A couple of months ago, I switched over to work at Tesla, and what I do is basically connect the guys that make the cars, or the people that design and engineer the cars, with the people that design and engineer the factories that make the cars. So we make the machines that make the machines. And one of those machines is this thing right here, which is called the Gigafactory. It's in Nevada. It's not that big right now. It's about 1/3 that size, but when it's built when it's finished, it's going to be the biggest building in the United States, bigger than the Boeing assembly plant in Everett, and bigger than the large vehicle assembly thing that NASA has down in Florida. So, and it is a monster equipment, sort of like lab space. Let's see if this plays. So this is kind of the making of the Gigafactory. So it's out in the desert in Nevada, outside of Lake Tahoe and Sparks. Oh, actually it's playing the, yeah, cool.
I got the sound.
You got the sound. We didn't really think about that. So it's a machine to make machines. So this factory makes all the batteries and all of the electronic motors, the electric motors to drive all the electric cars, so the Model 3s specifically. Heavily roboticized. Robotics are like very fetish-oriented thing, but there's a lot of people there too. There's about 12,000 people that work there on a daily basis, and people make things happen. Robots are super dumb. Like they do the same thing over and over again and very precisely, but people are adaptable. And so when things break down, you really need to put people on the problem. But as far as the building, think about like the densest lab building that you've ever worked on, or a hospital, and multiply that by like 100, and that's like the types of factories that we're dealing with here. Like that's pretty much what it looks like now. That's about a third of the footprint right there. And it is currently making enough batteries and motors to basically make all the Model 3s that we're creating right now, which are going to be probably 300,000 to 400,000 for this year. So we have a factory in Fremont, California, and then one that's being created in Shanghai, China as well. So these are all basically combining like the automotive design process with a fabrication assembly process, like making assembly lines, with the building itself all together, and obviously using a lot of technology for that. So a lot of Revit, a lot of Navisworks, a lot of CATIA and SolidWorks, and a couple other things like that. So a lot of inputs, a lot of outputs, and trying to optimize that, because if we can optimize that building process, that decreases the cost, and that makes it easier to build a lot more of these cars and sell them to people. So that's what we're trying to do there, by applying a lot of the things I talked about. So machine learning, AI, sensors, and all these other kind of things, on top of like massively large Revit models that that consistently like break people's computers. So anyway, so that's kind of the larger, highfalutin, hand-wavy part of the talk. Any questions about that so far?
That was a lot.
The large story arc of like, here are the big challenges we have. We have all the tools we need to help solve them, both for individuals and like your design firm, but also at the larger kind of socioeconomic and like kind of like society level.
Is there I guess you're going to show us, but is there a way to start to approach these things at, I don't know, our level? So, you know, for example, the energy modeling that you talked about, that it's easy to simulate the things that we know, but the things that we don't know, like people opening windows and that stuff. Is there either a product that exists or a tool that exists that can help us start to do more of that predictive analysis?
Haha. Yeah, there actually are. One's called Roast. It's made by Karen Timberlake. So it's like the ability to like have people not just through observational like sensor data, but like having people say, how do I feel? Like, am I hot? Am I cold? That kind of thing, and then feeding that back to a back-end database is like one way to do that. And you know, that's like we got taught at school how to do like post-occupancy analysis, and that's usually what people don't ever do unless you're designing and building a building. Like, you know, usually people move on to the next project, but if you can think about it as like an additional design sort of offering from your firm, is like we will help you understand how healthy your building is, or how occupiable it is, or what the behavior of your occupants are over time as an additional design service. I mean, that's another opportunity that people have, and that could be a reason to say like, hey, it's going to cost you another whatever, like, you know, $500 million to like instrument add like, you know, large sensor networks to your building or whatever like that. But the benefit of that is you can use that data over time to negotiate a better utility structure for the next 10 years of operation. Like, you know, those are the ROIs that we see people do. It's like, what's the first cost? And people usually balk and say, oh my gosh, that's a lot of money. But okay, you could use that information like downstream to not just have people be happier and healthier, but ultimately to save money is usually what it comes down to. So if you can equip, you know, your principals with like arguments in that kind of vein, then that could actually help you win work or make it kind of more approachable. And then the tools are there. I mean, there are tools out there. Like, I mean, there's no shrink wrap like Autodesk, like buy this tool, but there are things that are a lot more easy to get than they were even 5 years ago. They just might require a little bit of work to get them going. Any other questions?
Actually, I have a question related to data gathering. You know, as you mentioned, our firm does a lot of data gathering. One of the questions that we have to ask ourselves before performing an experiment is just what density of data is going to be relevant to us.
Yeah.
And I'm curious if, you know, I'm sure Tesla's collect lots of data. How many sensors do they have? 60 or 100?
We've got, so for, say that, like, I just did this math, like, so there's, like, just even from the mechanical equipment, like, forget about robots and stuff like that, like, there's, like 3,000 air handling units, say for example, just at a basic level, like in the Gigafactory now.
Right.
And each one of them has like 10 sensors on it, say for example, like for different pumps and temperature and all that kind of stuff. So I mean that's like the small amount of data representative. It's a large amount of data, but it's a small subset of like the larger data stream that's coming through. Yeah.
So is your position both in designing the factory and in designing the cars that you want to just get just err on the side of more density than you might need, and then subsequently sort of perform statistical models to figure out, okay, well, we can do away with these sensors because they correlate with these other sensors over here.
Yeah, I mean, generally, sensors are cheap. They're getting cheaper, and you know, building equipment manufacturers are increasingly adding sensors to anything that you buy these days. It's cheaper to collect the data, even if you don't know what you're going to do with it. Collect more, and then just sort of kind of decimate it down to whatever level of granularity you need after. I mean, hard drives are cheap. Databases are relatively cheap these days. I mean, yeah, you could be collecting like terabytes of data over time, but you know, well. So that's what we do. But it does turn into like you need different skills. You need like kind of data science background, and that's something that like, for example, like there's a software called Tableau. Have you guys heard of Tableau before?
Yeah.
They just got bought yesterday for $15 billion. $15 billion by Salesforce. Like that says a lot about like why data analytics and like visualization of data is like super important. Like holy crap, like $15 billion. Like I mean Power BI is like, you know, another one, but like throwing like a big database that even if you're not even like a database person, like collecting that data, talking to it and pulling it into a graph is like kind of one level of like it's sort of like knowing how to like get the basics done in any language. It's like sort of like the earliest level of like kind of information awareness and sort of like being able to understand the data, if not even to ask it the right questions yet, but just even like make some correlations. Like I see this trend line going up and this trend line going up. I don't know causation, but there's some correlation there. So yeah, so that's something that I would be curious to see how design schools and like sort of firms start to approach that, because it's still like kind of a black art, like dealing with like large amounts of data, and like because it turns into a math problem. Like I didn't do very well in statistics at all. Like I didn't really like any of the stats classes that I took or business classes, but they're actually fairly important these days. So anyway, so your questions, yeah.
Question about AI and machine learning.
Yeah.
So your friend and colleague did all the tree drawing.
Yeah.
And the computer interpolated that and then spit it out a bunch of different things.
Yeah.
What was the user interface used, and how can that be, brought to the masses to help just the general person who has a phone and that's about it? They don't really understand how it works, but it's like, is there, you talk to like a screen, or is it just like another tab on the ribbon? What's the...
Yeah, I mean, this is pretty much the interface. So he designed this thing as an iPad app. So this is running on an iPad, like full screen, and all it's doing is like it's talking back and forth with a server somewhere, but that's kind of irrelevant. It's just keeping track on the right-hand side of like, here's what you drew, here's what I came back with. So like literally the dialogue, almost like a chat session, like instant messaging. Here's what I said, here's what you said, here's what I said, here's what you said, back and forth to like kind of, and you can scroll back and forth through that. So it's super minimal, like doesn't require like a lot of other input at all, other than just drawing. And there's weird things that come out of it too. Like if you draw, like if you have your 3-year-old kind of draw some shape, it's gonna be like, I think that's a car, I don't know. Like, you know, like that, you get some weird, there's a bunch of YouTube videos out like that, like sort of these, like, yeah, type in like GAN, like generative adversarial network dreaming. Like there's these like what do computers think about like when they're dreaming, and it's like weird like visualizations of like literally the training sets that people are throwing at these things. So it's kind of a new area, but the interfaces, it actually simplifies the interface and makes it more design friendly, because you're not actually in this sort of like heavy like CAD environment, like you're literally just sketching like in 2D or 3D like on a flat tablet.
So he wrote the iPad program to do this?
Yeah, he wrote the iPad program and then the back-end sort of neural network to process the results. I mean, not just from scratch. I mean, there's a lot of these libraries that you can literally download that are like available now. But you know, trying to figure out like what to do on top of them is like is pretty cool. And there was actually there was a startup that was trying to classify architectural facades, and they got bought last year as well. So there's like more and more interest in this space along the way. So yeah. So any other questions? So these are all approachable. They're just like a little bit beyond like the normal kind of Revit or Dynamo or AutoCAD stuff that we're typically dealing with. But that's kind of where we see things going. But on a daily basis, yeah, pretty much. You know, my day job is like building buildings. Like I went from building software back to building buildings, but I build software to build buildings to make cars. So that's kind of like my full circle now. And the tools that we use are, you know, basically Revit and Navisworks and, you know, SolidWorks and Inventor and CATIA, things like that. And we are using things, a lot of Dynamo and a lot of Python, and that's kind of the next part of what we're going to talk about. But we can get up and like kind of stretch and get some other drinks and coffee or whatever. This can be interactive if you guys want, or I can just go through examples along the way. I'm happy to do either one, but you know, want to keep it interactive. I know it's a long day and it's getting a little warm here. So you can talk about HVAC. Like I think they turn off the AC usually like at 6 or so.
While we're doing this, I'm going to pass around the sign-in sheet. Just check your name off so that we can get you some credits if you signed up for that. But you just also want to know who's here.